Ever stop to think about those silent guardians in pretty much every building?
You mean the fire protection and fire alarm systems?
Exactly. Today, we're diving into a set of really informative slides that unpack these crucial systems. We'll look at everything from, the basic definitions right through to the specifics of building codes.
Yeah, our mission, really, is to cut through some of the complexity.
Right. And understand how all these interconnected bits and pieces work together to, well, safeguard life and property.
Couldn't have put it better. We'll kick things off by looking at what actually makes up a whole fire protection system.
Okay.
Then we'll get into that key difference between active systems, the ones that, do something when there's a fire, and passive systems.
The ones built into the structure.
Precisely. The ones that are part of the building itself.
Yeah.
After that, we'll zoom in a bit on fire alarm systems, looking at the components and why they're so vital for early detection and letting people know.
And we're not stopping there, are we? We're going to tackle building classifications based on the NBC 2016, the National Building Code.
We are. Understanding those categories is, well, it's key to seeing why different buildings need different levels of protection.
Makes sense. And finally, we'll look at some specific examples, right? Like sprinkler systems.
Sprinklers, fire pumps, hose reels, hydrants.
And even things like fire exit design, which is super important.
Which sort of brings us to a question for you listening in. Have you ever really stopped to think about just how many interconnected systems are working silently right now in the building you're in, all designed to protect you if a fire breaks out?
It's kind of amazing when you think about it.
It really is. It's this complex web of engineering and rules, and we're about to uncover some maybe surprising details you haven't considered.
Okay, so to kick things off then, fundamentally, what is a fire protection system? What are we actually talking about here?
Well, in essence, it's the whole setup, a
Yeah.
complete collection of systems and equipment,
Everything together.
everything. And it's all designed to do a few key things: prevent fires from starting in the first place, control them if they do start, and ultimately put them out.
And the main goal is always.
Always protecting lives, number one, and then protecting the property itself, the building structure.
Got it. And you mentioned these two broad categories, active and passive.
Yeah.
What's the sort of core difference?
The big difference is how they work. Active systems need some kind of action to function.
Okay, they need triggering.
Exactly.
Mm.
Usually triggered by the fire itself, like heat, or sometimes by a person. Think about sprinklers. They go off automatically when they get hot enough.
Right.
Or fire hydrants, which need firefighters to connect hoses and turn them on.
Makes sense. What else falls into active?
Oh, things like portable fire extinguishers, obviously.
Mm-hmm.
And then more specialized things like water spray systems or foam systems you might find in, say, industrial settings.
Okay, so they're the responders, the ones taking direct action. What about the passive systems then? It sounds like they're more about prevention or containment.
That's a great way to put it. Passive systems work because of the inherent fire-resistant qualities of the building's construction and the materials used.
So they're built in.
They are. Their main job is to contain a fire in the area where it started.
Stop it spreading.
Exactly. And slow it down. Examples: fire-rated walls and floors designed to resist heat for a specific amount of time. Fire doors are another big one.
Those heavy doors that often close automatically.
Yep. They're designed to seal an opening and stop flames and smoke getting through. Then you have fire partitions, smoke barriers to limit smoke movement, and the whole idea of compartmentation.
Compartmentation.
Yeah, basically dividing a building into fire-resistant zones using those rated walls and floors.
We've got some visuals here that help. There's one of rock wool insulation, so that's a key material for those fire-rated walls.
It is, yeah. Rock wool is very common. It's non-combustible, great thermal resistance. It really slows down heat transfer through a wall.
Okay.
And there's a picture of a fire door, too. Looks maybe like a normal door, but it's built differently.
Right, with special materials and seals.
Exactly. Designed to hold back fire and smoke for a specific time, maybe 30 minutes, an hour, even longer. Gives people crucial time to escape.
And this diagram showing compartmentation,
Yeah.
it really makes it clear, like creating boxes within the building.
That's the idea. Fire-rated walls and floors acting as barriers. If a fire starts in one box, it's much harder for it to spread to the next one quickly.
Contains the problem.
Exactly. Keeps it localized, hopefully.
That really clarifies the difference. Active fights the fire, passive contains it and slows it down. Okay, let's move to what often triggers the active systems, the fire alarm system. What's its main job?
The fire alarm system is, well, it's a vital subsystem within the whole fire protection strategy.
A specific part of the bigger picture.
Right. Its core job is twofold: detect a fire early ideally when it's just starting,
Yeah.
and alert the people in the building promptly. That early warning is absolutely critical
Why so critical?
because it allows people to start evacuating safely before the fire gets too big or spreads too far. It buys time.
Makes sense. And what are the key bits of tech that make this happen? The components.
Well, it's a network, really. You've got smoke detectors. They sense smoke particles, often the very first sign.
Okay.
Heat detectors, they react when the temperature jumps up quickly or hits a certain point.
Right.
Then there are manual call points.
The break glass things. Or pull stations.
Exactly. Fire alarm switches, pull stations, allows anyone who sees a fire to set the alarm off manually.
So, detectors and manual activation, where do the signals go?
They all feed into a central hub, the Fire Alarm Control Panel, or FACP.
The brain of the system?
Kinda, yeah. It monitors everything, processes the signals, and then activates the alarms, the sirens, buzzers, flashing lights, whatever notification devices are installed.
The things that actually tell people to get out.
Precisely. Signal the need for immediate evacuation.
So it's like the building's nerve center for fire. Sensing danger and then broadcasting the warning. We've got some examples of devices here. Fire Warden series detectors. What's special about those?
Well, the Fire Warden series and others like the multi-sensor detectors shown, they're designed for really reliable, very early detection.
Multi-sensor. Does that mean they detect more than one thing?
Exactly. They often combine smoke and heat detection, sometimes even carbon monoxide, in one unit. That makes them more accurate and less prone to false alarms.
Okay. Less chance of the alarm going off because someone burnt toast.
Hopefully.
Uh,
And then you see intelligent control and relay modules.
Yeah.
These allow for more complex control and linking the fire alarm to other systems.
Like shutting down ventilation.
Potentially, yes.
Yeah.
Or unlocking doors. And of course, the manual pull stations are there as that crucial backup. Human intervention if needed.
Right. Now, figuring out how much protection a building needs,
Right.
that's where the National Building Code, NBC 2016, and these building classifications come in, right? How does that work?
It's all about risk assessment, essentially. The NBC 2016 classifies buildings based on their main use, their occupancy.
What the building is for.
Exactly. Because different uses mean different fire risks, different numbers of people, different evacuation challenges. A hospital is very different from an office block.
Makes total sense. We've got the groups listed here. Group A is residential. That sounds pretty broad.
It is. Covers everything from lodging houses, single-family homes, right up to big apartment buildings and hotels.
Okay.
And even within Group A, there can be nuances depending on density and how people live there.
Then Group B is educational.
Yeah.
Schools, colleges, pretty straightforward.
Yep.
Group C is institutional. Hospitals, nursing homes, prisons, places where people might need help evacuating.
Precisely. The occupants might be less mobile or confined or asleep, so the safety requirements there are naturally very high, very stringent.
You can see why. Group D is assembly cinemas, stadiums, places with large crowds.
Yeah, large numbers of people, often unfamiliar with the layout, potential for panic, unique challenges.
Definitely. Group E is business offices, banks, IT parks.
Standard workplaces generally.
Group F, mercantile shops, malls, supermarkets, retail environments.
Correct. Group G is industrial factories, workshops. The risks there might be more about the processes or materials being used.
Flammable materials, maybe.
Could be, yeah. Or specific industrial hazards. Then Group H is storage warehouses, cold storage.
Less people, maybe, but potentially lots of flammable stuff packed together.
That's often the risk profile, yes. And finally, Group I is hazardous. Buildings dealing with highly combustible or explosive materials.
So the highest risk category.
Generally, yes, requiring the most specialized and rigorous protection measures.
It's clearly a very detailed system based on risk. So once a building is in a group, how does the NBC 2016 decide the specific requirements? It can't just be one rule for all Group E offices, surely.
No, absolutely not. It's much more nuanced. The occupancy type is the starting point, like we said, apartment versus hospital.
Right.
But then several other critical factors come into play. Building height is a huge one.
Taller buildings are riskier.
Generally, yes. Harder to evacuate, harder for firefighters to reach upper floors, so they need more protection. A 30-meter building needs more than a 10-meter one.
Okay, what else?
Occupant load, the number of people expected inside.
Makes sense. A packed concert hall versus a small villa.
Exactly. Higher load means more complex evacuation, potentially more fuel for a fire too.
What about the building itself, its size or how it's built?
Definitely. Building area, the size per floor matters. And the type of construction is critical.
You mean like concrete versus wood?
Precisely. Reinforced concrete frame RCC, versus a wooden structure. That determines the building's inherent fire resistance.
Okay.
Even the fire zone matters the risk category of the area within the city. Some areas are deemed higher risk than others.
Like densely packed urban areas versus rural?
Potentially, yes.
Yeah.
And finally, any special usage or hazardous content.
Like that generator room example.
Exactly. A generator room in the basement with fuel storage needs extra precautions compared to a standard apartment. Same if a building handles flammable chemicals.
Wow, okay, so it's a really layered approach. Occupancy, height, load, area, construction type, location, specific hazards.
It all feeds into determining the right level of protection.
Right. Let's dive into some of those active fire suppression systems then. Sprinklers first. We've got a schematic here, looks like a plumbing network.
That's a good way to think of it. It starts with a reliable water source, often a big tank.
Okay.
Then you need pumps to get the pressure right, usually a main sprinkler pump, and often a smaller jockey pump.
A jockey pump, what's that for?
It just keeps the pressure topped up in the pipes, handles tiny leaks without firing up the big main pump all the time, saves wear and tear.
Ah, clever.
Then you have the pipe network running through the building, usually hidden above ceilings.
And the sprinkler heads themselves?
Yeah, placed at strategic points.
Okay.
Each head has a little heat-sensitive element, often a glass bulb filled with liquid, or a metal link.
Right?
When a fire heats that element up to a specific temperature, exactly, the bulb breaks or the link melts, the sprinkler activates, and water sprays directly down onto the fire. The idea is to hit it early.
And we've got this fire pump sequence chart. Looks complex. Different pumps, capacities, pressure settings, why the different stages.
Okay, so this shows how they're designed to work together. The jockey pump, the small one, kicks in first for minor pressure drops.
Just maintaining pressure.
Right. But if the pressure keeps falling, like if a sprinkler head actually bursts, that signals a real demand.
Then the big guns come out.
Then the main sprinkler pump, with much higher capacity, automatically starts up to deliver the large volume of water needed.
I see other pumps listed too. Hydrant pump, diesel pump.
Often, yes. There might be a separate pump just for the fire hydrants, and a diesel-powered backup pump is crucial.
In case the power goes out during a fire.
Exactly. Ensures the system still works. The chart details everything: pump capacity, pressure, the head, flow rate, discharge, and the specific pressures they turn on and off at. It's all about efficiency and ensuring massive pressure is there when needed.
It's quite the system. And I see different types of sprinklers shown: pendant, upright, sidewall, concealed. Why so many?
It depends on where they need to be installed and how the space is designed. Pendant are the most common. They hang down from the ceiling.
Okay.
Upright ones point upwards. You might use those if there are obstructions below that could block the spray from a pendant head.
Right, like beams or ducts.
Could be. Sidewall sprinklers mount on the wall and spray outwards, often used in corridors or small rooms.
Where ceiling mounting isn't ideal.
Right. And concealed sprinklers are recessed into the ceiling with a cover plate.
For aesthetics.
Mainly, yeah. The cover plate drops off when it gets hot, then the sprinkler activates. Looks cleaner.
We also have this chart about sprinkler selection based on temperature different colored bulbs. That must be important, right? So they don't go off accidentally.
Oh, absolutely critical. That colored glass bulb is the heat sensor. It's designed to break at a very specific temperature.
And the color tells you the temperature.
Exactly. It's a standard code. Red is usually ordinary temperature, activates around, say, 68 Celsius or 155 Fahrenheit. Good for normal rooms.
But what if it's a hotter area, like near machinery?
Then you'd use a sprinkler with a higher rating, maybe a blue or a purple bulb, indicating it needs a higher temperature to activate. Prevents accidental discharges from normal heat, but ensures they go off in a real fire. Very clever. Okay, moving on. Fire hose reels. We see them everywhere. The diagram here looks pretty simple.
They are relatively simple, yeah. They give building occupants a way to tackle a small fire right at the beginning.
Before it gets out of control.
Hopefully. The diagram shows the key bits. The drum holding the hose itself with a nozzle, the connection flange, a landing valve to turn the water on and off.
The water supply connection?
Right, the waterway, the base, the arm, and the connecting pipe to the building's water supply. Readily accessible water.
And we have fire hydrants, internal and external. The diagram shows all the inner workings: handle, spindle, valve. These are more for the professionals, right? Definitely. Hydrants are for the fire service. They provide a high-volume water source needed to fight larger, more developed fires.
How do they work, basically?
Turning the handle wheel turns the spindle, which opens the main valve deep inside, letting pressurized water flow up and out through the outlets.
Where the firefighters connect their hoses.
Exactly. The outlets have caps to keep them clean. The diagram also shows accessories. Firefighters use special keys to open the hydrant, hoses, nozzles, extra valves.
We even have a schematic showing both sprinkler and fire hydrant connections integrated. It really is like a whole separate plumbing system just for fire.
It absolutely is a dedicated life safety utility. The elevation view shows sprinklers and hydrants on different floors, all connected.
And Detail A shows close-ups of sprinkler pipe components.
Yeah, things like the main control valve to isolate sections for maintenance, a flow switch.
What does the flow switch do?
It detects when water is actually flowing through the sprinkler pipes. Sends a signal to the fire alarm panel, tells you the system is likely activated.
Ah, okay. Important information.
Very. Also shows test valves, sight glasses to visually check flow, pipe unions for easier installation.
And the plan view.
The layout shows the water tanks, the pump room, and how the pipes run to feed all the internal and external hydrants and the sprinkler zones. You see the valve symbols used on drawings too.
The level of planning is incredible. Okay, let's switch back to the fire alarm system connections. This diagram shows the main panel linked to lots of devices. Looks like there are different ways they connect.
Yeah, the connection method is key. The diagram shows two main types of circuits. First, an intelligent addressable detection loop.
Sounds fancy. What does addressable mean?
It means each device on that loop, every smoke detector, heat probe, even maybe a monitor on a valve, has its own unique digital address.
Like a house number.
Kind of. So if a detector activates, the control panel knows exactly which one it is and where it's located. Pinpoint accuracy.
That must be hugely helpful in a fire.
Invaluable. Compare that to the second type shown, conventional detection zone.
How are they different?
In a conventional system, you have multiple detectors wired together in one zone, like one circuit covering a whole floor area.
If one goes off.
The panel just tells you there's an alarm somewhere in that zone, not with specific device. Less precise.
Big difference in response time, potentially. What about these other things connected? Loop-powered sounder beacon.
That's an alarm device, a siren or flashing light, that gets its power and signal directly from that same addressable loop. Simplifies wiring.
Okay. And this Wagner aspirating system.
Ah, that's a more advanced type of smoke detection. An aspirating system, someone's called air sampling.
How does it work?
It actively draws air samples from the protected area through a network of small pipes. It constantly analyzes that air for tiny smoke particles.
So it can detect smoke even earlier than a normal detector.
Potentially, yes. Much earlier warning in some cases, often used in critical areas like data centers.
Got it. And the diagram also shows outputs for bells and sounders and relays for things like doors and shutdowns.
Right. The programmable monitored outputs trigger the main alarm bells and sirens. The programmable VFCO relays, voltage-free changeover relays, are used to control other things, maybe automatically unlock fire exit doors, or shut down the air conditioning system to stop smoke spreading.
So the fire alarm talks to other building systems.
Yes, integration is key. And that final schematic, monitoring and controlling by FACP, really emphasizes that.
How the panel watches over the suppression systems, too.
Exactly. It shows detectors, but also monitoring devices on things like sprinkler valves, all feeding back to the panel via those loops. It confirms if the sprinklers are actually flowing water, for example. Gives a complete picture during an emergency.
We spent a lot of time on the active systems, which makes sense, but passive fire protection, that's just as vital, isn't it? The built-in stuff.
Absolutely fundamental. Passive protection is about containment, stopping fire spread, protecting escape routes, and keeping the building structure stable long enough for evacuation and firefighting.
It buys time.
Loads of time. And it relies on the building's design and materials, which brings us back to those type of construction categories from NBC 2016 Part 4.
Right, we have that table. Type 1 was very strong, 4+ hours fire resistance, concrete, protected steel. For high-rises, important buildings, the top tier.
That is the most robust. Then Type 2 is strong, 3+ hours resistance, still using concrete, masonry, steel. Good for medium-rise apartments, maybe.
Okay. Type 3 is moderate, about 2 hours resistance, might have some wood, suitable for smaller offices, villas.
Yeah, some combustible materials might be involved, but still offering significant resistance.
Yeah.
And Type 4 is low, less than 2 hours. Mostly wood, lightweight stuff. Think temporary buildings, maybe farm structures.
Speaking of escape routes, fire exit requirements, obviously crucial. NBC 2016 Part 4 again, and it seems heavily based on occupant load.
Yes, the number of people is the starting point for designing exits. How many people need to get out?
How do they figure that out?
The code gives occupant load factors based on the building type. For residential, Group A, it's 12.5 square meters per person.
So you divide the floor area by 12.5.
Basically, yes. That tells you the minimum number of people the exits need to be able to handle for that area.
We've got that calculation example, 10,000 supplementary building, 10 floors, gives 800 people total load, 80 per floor.
Right. And that number then dictates things like minimum widths for stairs and corridors.
Yeah, it says minimum 1.0 meter staircase width for apartments, but 1.5 meters preferred for high-rise, and 1.2 meters for corridors, again 1.5 preferred if it's high-rise or busy.
Those widths are critical for smooth, quick movement of people. No bottlenecks.
And the code also specifies the number of exits needed.
Yes. Based on that occupant load and capacity factors from Table 4 in the code, it tells you how much width you need per person for stairs or ramps.
So enough exits, wide enough exits. What about where they are placed?
Also critical. Arrangement is key. Exits need to be located so the travel distance to reach one isn't too long.
How far you have to walk to get to safety?
Exactly.
Hmm.
Table 5 gives limits based on occupancy and construction type, and they need to be remote from each other.
Why remote?
So one fire can't block all your escape routes. You need alternative directions to safety, and it limits dead-end corridors too.
Places where you could get trapped.
Right. Maximum length is usually 6 meters for places like schools or hospitals, maybe 15 meters for others.
Finally, it gets into specifics for staircases. Minimum of 2 in nearly all buildings.
Wow.
Yep, redundancy is key. And they need to discharge safely at ground level, either directly outside or through a protected passage or a large lobby.
Not just dump you into another potentially dangerous area.
Exactly. At least half should go directly outside or via a passage. And the stairs themselves need to be built of non-combustible materials. Minimum 120 minutes fire resistance.
2 hours of protection for the escape route. That's the idea. Minimum width for residential is 1.25 meters. Handrails are specified too, one side for narrower stairs, both sides if they're 1,500 millimeters or wider.
For support. And basement access.
Must be via a separate stair, isolated from the main escape stairs. Don't want basement fire smoke getting into the primary escape roads.
That makes sense. And external stairs have their own rules too.
They do. Must go straight to the ground, separate entrance from internal stairs, non-combustible doorways. Onto them need that 120-minute rating.
And not too steep.
No steeper than 45 degrees. Minimum width, 1,500 millimeters. Handrails both sides, specific height range. All designed for safe, reliable escape.
That is an incredibly thorough look at fire protection and alarms. We've really unpacked the key parts, haven't we? Active versus passive, how the codes like NBC 2016 dictate needs based on so many factors.
It's fascinating when you drill down, isn't it? Even things like the different sprinkler head types, each designed for a specific job, or that whole pump sequence.
Yeah, the network of pipes and pumps working together.
It really highlights the amount of thought and detailed engineering that goes into protecting buildings,